So what I want to discuss is spatial correlations in these ground motion simulations. And I want to talk about it from the perspective of validation. I think this is a metric we can use in these validation exercises, as well as an opportunity to push forward our, our analysis and earthquake engineering in ways that we can't achieve with empirical ground motions. And I'll look at the CyberShake simulations in particular, but some of these issues all these issues are relevant more broadly. And this is work done by Yulin Chen, who just finished his PhD a week ago. So I'm giving him a break and speaking on it, but it's his work. And then I'll also thank SCEC and USGS for the financial support for this work over the past few years. So first, let me talk for a couple slides about spatial correlations and mathematically what I mean when talking about these spatial correlations and ground motion amplitudes. And I'm going to start with recorded ground motions as motivating data, and then shift over to simulations in just a moment. So if we take a set of a well-recorded events, so this is a map in the lower left of observed 1 second spectral acceleration amplitudes from the 1999 GT earthquake, which is nice since we have so many recordings. So we can think about the observed amplitudes, and that's plotted in color scale on this map. And when we try to predict these ground motions using an empirical ground motion model, we break this down into kind of a prediction of the mean of the log of the amplitude. So that's in this middle map here, where we have basically we're reflecting the attenuation of amplitudes with distance and some impact of side effects and anything else that might vary spatially. So we predict smaller amplitudes more distant from the rupture, and that the surface projection of the rupture is approximately noted with this gray rectangle. Then we have a between event residual that's constant for all of the recordings in the event, so that's not as much interest to us here. But we also have these within event residuals. And so for observed ground motion data, we can take our observations, subtract off the predictions, subtract off the between event residual, and we're left with these within event residuals, which tell us how strong was the observation relative to our prediction. So looking in this lower right figure, kind of at the north of the island, we've got this big cluster of red circles. These are positive residuals saying that the observations were stronger than our model would predict. And then say to the west center of the island, there's a bunch of cool colored recordings indicating that the amplitudes of the recordings were less intense than we would predict. And so we see the spatial clustering of these colors, as we would expect physically, that when we see strong amplitudes in certain places, we would expect in neighboring locations to see similarly strong amplitudes. And so that's what I'm referring to with these spatial correlations. Right? So the spatial attenuation of amplitudes is already covered by kind of mean predictions, but there's this unexplained variability that has spatial correlations in it. Let's do one more slide about recorded ground motions. So when we're trying to estimate these empirical correlations, estimate these correlations from empirical data, we don't have kind of repeated observations of the same earthquake at pairs of sites. So what we'll do is we'll make the stationarity assumption that says all stations with equal separation distance, let's assume them to have equal correlation. And so schematically, I've got 3 arrows drawn here on the map of pairs of stations with the same separation distance. And we could go through the map and find all the pairs with the same separation distance and call that distance h. And so then we'll have n paired observations, and we can compute a correlation between those n observations. And that's plotted over here on the right with blue circles. This is actually a variogram, which you can think of as kind of the inverse of a correlation. But we can repeat this process with all different separation distances, measure the dissimilarity of the observations, and then we can kind of get this trend that we see in the blue circles, and then we can fit a model through it with that black line in the right figure. And so that's this kind of bootstrapping on top of the data where we pair up all these stations, allows us to estimate how similar would the amplitudes be at a given separation distance. But it requires us to assume that kind of all pairs of stations with the same separation distance have equal correlation. And that may not be true for a variety of reasons, as we'll talk about in a moment. And so that's kind of traditionally how this spatial correlation, these models have been built up. And this has been done for a couple decades now. And this spatial correlation is important from an engineering perspective because it influences risk to spatially distributed systems. So kind of a quick one-slide explanation of what's going on. This is kind of repeating some work from a former student in MLJRM a decade or so ago. So he was looking at disruption to the transportation network in the Bay Area and was simulating kind of earthquake events and then the spatially distributed ground shaking amplitudes that would result, and then the disruption to the transportation network given that ground shaking. And he went through the exercise with different permutations of ground motion models. So the right figure shows the results. So the horizontal axis is kind of a metric of how disrupted the network is. And then the vertical axis is how frequently that level of disruption happens. And the top blue line is what we think the right answer is with respect to these models. So we've got that spatial correlation in the ground motions included. The red line on that figure is the same set of simulations. We simulate the same earthquakes. We simulate the same mean amplitude for each earthquake and the same variability of the amplitudes. But from station to station, we don't put any spatial correlation. So if the ground shaking at one bridge was stronger than expected by a ground motion model, the bridge up the road, we have an independent draw of that variability. And it lowers the line. And that's because the kind of highly disrupted earthquake scenarios are the cases where we see damage to a large number of bridges in the same spatial area that really disrupts rerouting and things like that. And you don't get those extreme kind of clusters of damage if you don't have the spatial correlation in the ground motions. So to be clear, that red line is, we don't think it's the right answer because we've taken out spatial correlations that we see in real ground motions, but it's a sensitivity to study to understand that those spatial correlations are important for distributed risk analysis. So now let's switch to simulations. So with that as motivation. So I want to look at the CyberShake simulations, and I've heard lots about these. I don't think I need to give much detail, and we're strictly consumers of these simulations, not producers. But we're using the version 1512. So this is the wave propagation through 3D crustal velocity model in Southern California. And there's about 400,000 rupture simulations and ground motion time series at 336 stations. So the maps at the bottom show the locations of the stations. And these are 3 of many realizations of a Puente Hills rupture underneath downtown Los Angeles. We've got on the order of dozens of simulations of the same rupture geometry, where just the slip amplitude and direction and timing and spatial variability, those are randomly sampled, but the geometry of the source and the magnitude of the event is held fixed. And for each of these earthquake simulations, we can observe the ground motion amplitudes. We take the average of all those amplitudes as kind of the pseudo mean prediction, and we see how much does each simulation vary relative to those mean predictions, and that's what's colored in these maps. Right? So we get, the interesting thing is we have multiple realizations where we've got kind of nominally the same earthquake in terms of the magnitude and distance metrics and things that we usually use in engineering. And so the question is, what can we do with those? So the first thing we can do is do some validation. So what we did is we took those maps of the ground motion residuals, and we did the same spatial stationary correlation estimation. So what these figures show, we would take the left figure, we took about 100 magnitude 8 San Andreas ruptures from the CyberShake database, and we did that spatially stationary correlation estimation. And the triangles on the figure are kind of interesting. So we get this kind of decay in correlation coefficient versus distance, which is the horizontal axis. And then the lines, all the solid and the dashed lines, those are 4 empirical models fit by various people over the years to observational data. And so the takeaway here is that those triangles are in the neighborhood of all the empirical models. So maybe a little bit higher correlation at distances of 10 kilometers and kind of very strong agreement out past 20 kilometers. Did the same exercise with some Puente Hills ruptures on the right figure, and there the observational correlations from the simulations match very well with all the empirical models out to 30 kilometers and dip down a little bit. Some of this is just small sample variability of things, but the point is that the correlations are largely consistent with what we see in empirical ground motions. And so that means that the things causing the correlations are to some extent present in the simulations. And so I think this is an interesting validation metric. We can do this relatively direct comparison between empirical data and simulations with this type of scoring. And when we're trying to use simulations for distributed infrastructure risk assessment, we know this is an important metric for us. Okay, but we can go a lot further than just this kind of direct validation calculation, because there's a lot richer data set with the simulations. So what we did with the simulations is we said, look, I can take 2 specific sites, and rather than mixing together all the sites, let's take a specific site A and a site B, and then let's take like n realizations of a rupture. And we've got kind of n realizations of paired residuals that we can then just directly compute a correlation coefficient with. And so for these 2 specific sites and this specific rupture geometry, we can estimate a correlation. And if we do that, we can see some interesting results. So here's the CyberShake study area. The triangle is kind of our reference site. And then for all the other locations in the region, we're going to compute a correlation coefficient. So this first figure is just a reference model, one of those empirical models. So there's just a spatial decay in kind of bullseyes around the triangle in spatial correlation. This is data from CyberShake simulation. So we see a little bit different pattern. We don't just see kind of rings around the triangle. If we move around the reference site, the pattern of kind of the red colors, which is the high correlations, that changes around a little bit. And I should note these are all for San Andreas simulations, and the surface projection is noted with the black lines kind of up to the northeast of the map. There's interesting things going on here. There's kind of path effects. There's also 3D crustal wave propagation effects. So through things like the LA basin, that's kind of an area of these. And so we tried to kind of pull out some pairs of ruptures and sites to see what's going on. You can see some evidence that maybe the source and the direction of kind of wave propagation from the source is important. So here's on the left, a Puente Hill simulation with a reference site kind of over the south edge of the rupture projection. And kind of all of the locations to the south of the rupture are very highly correlated. And the locations on the opposite side of the rupture are negatively correlated. So indicating kind of a potential for bilateral ruptures giving, for unilateral ruptures giving kind of strong amplitudes in one direction and weak amplitudes in the other. It would cause a negative correlation. I'm moving along through a couple of these others. So you can see some path effects. So here on the left figure, this is a kind of a rupture off to the far east of the study area, a reference site down in the LA basin again, and you can see this kind of strong trend of red colors indicating maybe some kind of focusing into the basin in the area. And so some indication that velocity model is giving us spatial correlations with interesting patterns. And so those are anecdotal, and what we wanted to do is think about, systematically, can we identify areas where there's some richer correlation structure? And so Elin came up with this approach that we just published about a month ago to build correlation graphs and look at it. And let me talk you through briefly how we do it. So in this figure to the right, each black circle is a station. And so this is just a schematic idea. We can think about kind of having these 6 stations. And between each pair of stations, we can compute a correlation coefficient, as done before. And so, in the schematic diagram, there's kind of 3 stations off to the left with high correlations, and some stations off to the right with high correlations. And then, between there's different numbers. But we expect that kind of the close together stations would be highly correlated already, like a stationary model would give us this. And so the question is there a deviation from that model in this type of correlation data? So what we do is we take that global correlation model, like the stationary model, and we predict what do we think the correlations would be between each set of those stations using that generic model. And so that gives us kind of a model prediction we can compute a deviation from. And then we can take the deviation between the two of those. So because these are correlation coefficients, we do this kind of Z transform on them to normalize them. And then there's kind of a normalization by the number of observations you have to kind of measure out, is this deviation likely or unlikely under a finite set of samples. So you can compute this deviation. It's kind of should be standard normal, and you can get these numbers of the deviation. So in this case, I've drawn in with kind of red arrows the cases where we have stronger correlation than the global model would predict, and then in blue we have pairs of stations with weaker correlation than the model would predict. And then we can do some clustering on that. So we tried some different clustering techniques. It turned out this sign spectral clustering was a good strategy. So what we're trying to do is we're trying to find, we can represent all those arrows with a graph, and we're trying to find kind of links in the graph that have these high deviations, and we want to try to find clusters in the graph that all have high deviations. So we want to end up with a picture like in the bottom here, where we have kind of a cluster on the left, and within that cluster, the arrows tend to be red, and then we have a cluster on the right with a lot of red arrows, and then the arrows crossing between clusters tend to be low. Right? So we want high correlation deviations inside the cluster and low deviations across the clusters. And so this sign spectral clustering is an efficient algorithm to get at that. So what we did is we computed a correlation graph using the CyberShake data and then ran this sign spectral clustering. We tried a bunch of other techniques too, but found this to be the most reliable. So we can look first at these kind of Puente Hill simulations. Right? We can see, to the south, we have this kind of grouping of high correlation sites, and to the north, we have the kind of negative correlations with these southern sites and things like that. We want to get at that more systematically with this kind of 335 station by 335 station matrix of correlations. We wanted to pull out kind of the interesting pairs. And so here's what we see. This is run on the Puente Hill simulations. So the left map is, we've got symbols indicating all the station locations, and the symbol style and color is varied by clusters. So the algorithm kicked out 4 clusters in the end once we tuned it up a bit. So we've got kind of cluster 1 off to the far west with the blue circles, clusters 2 and 3 off to the east, northeast, and then cluster 4 down, approximating the LA basin or to the south of the Puente Hills rupture that this data is coming from. So on the right, we've got all those stations, their correlation deviations plotted in this grid. So the XY coordinate in the right figure indicates a pair of stations, and then the coloring of that pixel indicates whether those stations have kind of a high deviation or a low deviation. And the stations are ordered by these clusters. So the top row is kind of cluster 1, then cluster 2 and 3 and 4. And so what we see is this kind of strong block diagonal set of red colors down the diagonal. So cluster 1 within itself, those stations tend to have higher correlation than our global model would predict. Clusters 2 and 3 kind of effectively all blend together. So even though the algorithm picked out 2 clusters, even between clusters 2 and 3, there's also very high correlation. And cluster 4 has got red, but some blue mixed in it. And then off diagonal, we've got lots of blue because we see those low correlations across clusters. There's also some big patches of white here. I'll say when we had stations more than 100 kilometers apart, we didn't include them in the graph they were a little noisy and we didn't expect to see any correlation. So we just pulled those out and now leave some white in the graph. And so it's kind of interesting. And I guess if we then take those 3 groups, if we merge clusters 2 and 3 together, and we compute correlations within those communities, we get models like this. So the blue line indicating community 1, we've got this very high correlation that's decaying more slowly with distance. The black line is our kind of global correlation that's lower. And then the dashed black line is the correlation when we cross communities, and that's even lower. And so it suggests there is this structure in here that's persisting across these simulations. And some of it is
2 minutes.
Great. Some of that is rupture geometry related. We saw that kind of north versus south pattern. Some of it we suspect is maybe related to kind of 3D crustal structure. Maybe that cluster 4 could be a little bit related to that. But because it's a relatively deterministic simulation, you've got chances to kind of explore these patterns and look at causality. So to start wrapping things up, I have kind of 3 points to leave you with today. So the first is that these spatial correlations and ground motion amplitudes, they're important for regional risk analysis problems. And I think they're a useful target for simulation validation. And so we've done some of this work. There's groups in Italy that have done a little bit of work as well with validation of simulations for spatial correlations. But I think there's more opportunities to look at this and run more algorithms through this type of calculation. Second point is that when we do the stationary correlation estimation, we do see consistent correlations with empirical data. I should say this is at long periods, right? So we're only using kind of the deterministic portion of these simulations where the wave propagation should produce stationary correlations. At the short periods, because the algorithms are different, it's not as clear what's going to happen there. So we were really focused on the part where the physics is constraining the simulations. And then the third point is that beyond the direct validation in comparison to empirical data, I think we can see some really interesting pair-specific correlations in here. And this is not I don't have results for you here, but I think there's hints at some interesting causality. Right? Is it wave propagation effects? Is it effects in the randomness of the rupture itself, producing kind of pockets of high and low amplitudes nearby the rupture, things like that. And I think this technique we've come up with to find these high correlation communities will let us systematize those explorations further. And so I think there's interesting opportunities here. And as a consumer of these spatial correlations for regional risk analysis, if these kind of non-stationary effects are real in ground motions, which physically I would expect they are, we need to be thinking about how to be pulling that into our risk analysis and not just using the simplified models that we can build from empirical ground motions. So I think that's another great opportunity moving forward. And finally, I'll note my website's down at the bottom there. The papers from you and China are all up there if you'd like to read in more detail about some of the things that I've highlighted today. So that's what I have. Thanks very much for your time. Appreciate the opportunity.
Thank you, Jake. This is very interesting talk.